Now we are to begin chapter 10 on infinite sequences and series. So at this stage in your math career, it's you may or may not have seen much information or content on sequences or series. If you've done college algebra, we do a little bit of it at the very end. So I'll treat it as if you haven't. So the beginning, it might seem very familiar, and then we'll get into stuff that's probably not, which is the goal really is more towards series, and just recall a series is a sum, which you may or may not have seen, but it's the summations. We'll get to that later in the next couple of sections. And we're mostly interested in the sum of these sequences, but we got to define sequences first. So, and whether or not those series converge or not. So we'll have a bunch of convergence tests for summations is the ultimate goal. So first, let's talk about sequences in 10.1. So go ahead and write all this stuff down. So let's get rid of that. I don't really need that now. So the notation looks like that. We use A for usually terms of a sequence, or maybe B. And then you have subscripts. You have these subscripts like this, 1, 2, 3, etc. So this is the definition. Let's maybe go ahead and put it like this as a definition of a sequence. So a sequence is a function whose domain is the set of positive integers, or we could call them naturals. And you could start actually at 0, so you could have whole numbers. You can actually start negative values and then define it that way. But in reality, we're mostly interested in what happens as you approach infinity most of the time. So these are infinite sequences that we're actually mostly concerned with. So let's, so the function notation we're used to would be, oops, I'm going to mess that up too in this. These are rough, going to be pretty rough videos. I'm not going to edit a lot, so bear with me. It's taking a while. So f of 1, f of 2, f of 3 is the values we're inputting. And you go on like that kind of indefinitely. We say f of n, right? So we call these terms of a sequence. So this would be the first term, second, third, and this we say is the nth term of the sequence. So nth term. So it's a function, but we don't usually use that f notation. We use a or b, sometimes c, to determine or write the sequence. So let's look at an example of a sequence, some other notation to look at. So the other notation would be kind of like this, it almost looks like a set, but it implies that it's a sequence. So that's like you would say the sequence A sub n. So let's suppose the sequence A sub n is just 2n, like that. Then as you input the n, so as n goes from 1, right, indefinitely to infinity, approaching infinity, then you have the different, what we say, terms of the sequence. So the fifth term would be 10, right? So if you listed out the terms, you'd have 2, 4, 6, 8, etc. So what type of sequence is this? What would you call those? Hopefully you all answered. Those are even integers. So that's the sequence of just even integers. You can do odd, so those are evens. Let's define another one. Maybe we'll use b sub n. So suppose b sub n are odd integers. Odd integers can be written as 2n minus 1, like that. And so if you listed out terms, if you put in 1, you get 2 minus 1 is 1. So you get 2, 3, 5, etc. So those would be odd integers. All right, so this those are different examples. And if you look at the book, there's a number of them to describe. Let me show you a couple more. We'll look at the sequence. It's kind of a nice little chart I found here. A different book. And then you can write or call the nth term A sub n. Then we'll do the first 4 terms. And then we'll do the 10th term. Just to give you some ideas in case you hadn't seen this ever before. So here's one. So if you have n over n plus 1, that is a notation for like the entire sequence. The nth term is just the what's inside, basically. It's just the n over n plus 1. It's like the function that you're substituting in the variables, the independent variables. First 4 terms would be a half, 2/3, 3/4, 4/5, etc. And we're interested in really what that converges to. So as you take a limit, what does it converge to? 10th term is just 10 over 11. All right, so there's an idea of one. Let's do one like this. You can make the terms alternate signs. So if we did -1 to the n plus 1, then that would be, times n squared over 3n minus 1, like that. And then I won't waste my time to recopy that. I just realized I can copy this as I was thinking about it. So that's the nth term, of course, just the inside part. And then the terms of the sequence, you're just evaluating again for your integers. So your positive integers, you're putting in 1 through infinity. And you'd have 1/2 again. And the next one's going to be a negative 4/5, 9/8, negative 16/11, etc. The 10th term, you're plugging in, substituting in directly, just n equals 10. These are what are called explicitly defined sequences. It's explicit. You substitute a number, you get the term out. Let me show you another case, and we don't really work with these a lot, but it's worth showing what this one is. These are called, so this is what we call explicit. Let me write this over here. So this is explicit or explicitly defined sequences. The next one I want to look at are what are called recursively defined. So recursively defined sequences. So this is the case where they give you multiple terms, and then the next term or the next maybe couple terms defines the next term. So let me say that again. So the first couple terms define the next term. So for example, if I say A1 is equal to 3, so they have to tell you like the first term, then the next term, A sub k plus 1, is equal to 2A sub k. So it's twice the previous. And then we can say for k greater than or equal to 1. and it's implied that k then is 1, 2, 3, etc. So you're putting in just integers into the sequence. So if you listed them out, A1 is 3 is given. A2 is just going to be 2A1, which is 2 times 3, which is 6. And then A3. A3 is going to be 2 times 2 times 3, which is 2 squared times 3, which is equal to 12. And you could keep going, but spend a little time to look at this. You can define your nth term. Your nth term is just 2 raised to 1 prior, so that's a 2, that's a 3, so it's 1 less than the power. So it's 2 to the n minus 1 times 3. So you have a recursively defined case here, right? But then in some cases, not all cases, but in some cases you can define the function explicitly like this. One very somewhat famous case is if you define Fibonacci sequence. So Fibonacci sequence is defined to be recursive. It's a recursive definition. Excuse me. Okay, so let's continue. So a lot of just definitions and examples, kind of just getting warmed up here as we go. So it'll be a little chunky video as I go wade through stuff. Let's look at the definition of limit. So let's jump into that. Okay, so here's the definition. So this is kind of some more heavy-duty stuff that we need to know. A sequence, and I'll just abbreviate like that. A sequence A sub n has a limit L or converges to L with a notation looks like this. So we say the limit of A sub n as n approaches infinity equals L. That's good enough. Well, I'll just write it out for you. Or A sub n approaches L as n approaches infinity if for epsilon greater than 0 there exists, remember the backwards E means there exists, a n greater than 0 such that absolute value of A sub n minus L less than epsilon. Actually, let's write this as an implication instead. Usually, they may reverse that in the book, but it's n greater than capital N implies that absolute value of A sub n minus L is less than epsilon. So basically what it's saying then is eventually, if you keep going, then there's going to be a value that after that value n, let's think of n as being a fixed value. After n, you can get as close to L as desired because epsilon is arbitrary. So you can get as close to L as desired if you just go past capital N. All right, so then if that's what you get if it exists, if it has a limit, if the limit doesn't exist, so if L doesn't exist, we say it has no limit or we say it diverges. So let's just write that down. So if L does not exist, then we say no limit, or we say it diverges. Which I don't think we used that notation before. We would just say a D and E. We often just said it's a D and E, but now we're approaching infinities, so we're talking about divergence. And it may diverge or go off to infinity, right? Or it may like just bounce between like -1 and 1. It may just go up and it just doesn't converge to any place. We're talking about it converging to a value. And I'll draw some diagrams a bit later when I get to it. Alrighty, so let's continue. So let's see. I think I was about ready to do that. Let's get rid of some of this stuff. I'll talk about that in a second. So let's draw this picture. You may have seen this before in Calc 1. So if you have this sequence, you can graph these, but they're not very interesting to graph because your inputs are just 1, 2, 3, 4. It's not very interesting. So you're putting in 1, 2, 3, 4, 5, etc. like this, and then you have just dots in your graph. So let's suppose some sequence is going to converge to this value L. Then you'll have the L plus epsilon maybe up here, and then down here will be the L minus epsilon, a little less. All right, so then let's just make this, so this is what you're going to converge to. Let's suppose it does that. So that's your tolerance. Sometimes they talk about tolerance like that. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right, 12. And you may, so your first point may be here, your second point may be here, third point may be here, and then eventually it's going to be within that, but not come back out of it. And that's 5. Maybe it goes up like this, and then back down. Oops, missed a spot. So then it eventually goes like that. So these inputs, and it'll be kind of hard to draw. Let me see if I can zoom in a little bit. So this is 1A1. This would be 2A2, etc. Each of those points does that. And so that's what the graph would look like. It's not a very interesting graph. Maybe I can make it interesting by maybe coloring it in, maybe doing a dot, I don't know, red dot. So red dot like that. Okay, this was not supposed to be there. All right. So that's what we mean by convergence. All right. So here's a theorem that helps us determine whether a sequence converges or diverges. It's actually basically just taking a limit like we have done before. So this is a theorem, and I'm not going to label the theorems. I'm not directly following what the book has, but I'll cover everything what the book has eventually. So let's look at this theorem. Let A sub n be a sequence. Let f of n equal A sub n. And that's just notation right now, but we're going to convert that to reals. And then let's say, and suppose f of x exists for all reals. Okay, don't finish up our writing here. So for all x in R. Actually, we want to make it greater than 1. For all x greater than or equal to 1. So we're basically going to say, for sequences, yes, we know it's just natural numbers, 1, 2, 3, etc. But now we're going to say, let's define a function that matches the sequence, but let's put it in the reals instead, at least after or beginning at 1. So if you have that, we have two cases. One, if the limit of f of x as x approaches infinity equals L, then the limit of f of n as n approaches infinity also equals L. So what it's saying then is if the limit is true or exists in the reals starting after 1, then so does the limit as you approach infinity for the naturals, or for as n approaches infinity. So those are the positive integers. So if it works here, red dot, if it works here, it works here. So all the techniques we used for taking limits before as you approach infinity will work for these sequences, which is nice, at least for this section anyway. And then also if it diverges, then it also diverges. So that's the second piece to this. So if the limit of f of x as x approaches infinity equals, I'll just say plus or minus infinity, then so does the sequence. The limit of f of n as n approaches infinity equals plus or minus infinity. They match. It's not like minus plus or anything. They actually match. So let's take a look at this example. If a sub n is equal to 1 plus 1 over n, determine if the sequence a sub n converges or diverges. So we can let f of n equal 1 plus 1 over n. For f of x equal to 1 plus 1 over x, we can take a limit. As x approaches infinity. So we can just investigate that. So it's a limit of 1 plus 1 over x as x approaches infinity. So that's 1 plus, and then we know that 1 over x approaches 0. So it's 1 plus 0, which is equal to 1. Therefore, the sequence, just say a sub n approaches 1 as n approaches infinity. Or we could say it and just write that out. We could just say the limit of 1 plus 1 over n as n approaches infinity is equal to 1. And really it turns out that you don't have to write x in there. You can just investigate like you normally do. The only issue might be is if you start taking derivatives, because derivatives are defined on a continuous function on the reals. You can't really take a derivative for the naturals, but in which case we're talking about like L'Hopital's rule. So if you have to apply L'Hopital's rule, you really need to switch to the real valued form. Some other notation concepts or terminology, we would say the sequence a sub n converges to 1. That's how you would state that or say that. Okay. Let us continue. Let's talk about monotonic. So, some more definition stuff. So we're going to define a monotonic sequence. So a sequence is what we say monotonic. So like the root wording there is monotone, so one thing. So, but a sequence is monotonic if successive terms are non-decreasing or non-increasing. So non-decreasing or non-increasing. Oops. So monotonic sequence basically would be A1 is less than or equal to A2 is less than or equal to, and it continues like that indefinitely. So it's basically, in other words, what we would say is it's always increasing or it's always decreasing. So one or the other. So either they don't bounce around. They don't go from here to here and then back like this. It's always increasing or always decreasing. So that's the concept. So let me write the other way. So the other way would be A1 and then just greater than or equal to A2, which is greater than or equal to, etc., greater than or equal to A sub n, greater than or equal to, etc. So that's monotonic. So always increasing or always decreasing. So let's draw a little picture of this one just to be clear on what we're saying. So for this one, A1 is less than A2. This would be an increasing sequence. So it would look like this. This would be a decreasing sequence. So it might look like this. Okay, so it's at least always decreasing or always increasing. Next definition is bounded. So we say a sequence is bounded if there exists m, which is positive, so positive real number, such that the absolute value of a sub k is less than or equal to m for all k. We'll say all k greater than or equal to 1, to be clear on what we're talking about. So let's look at an example of this one. So we already talked about this one. So we look at n, so for example, n over n plus 1. What does that basically approach? So the concept is that there's an existence of some value that bounds it. So it's not greater than this value or less than this. It's less than this value. Sorry, it's less than this value for all k eventually. Right, and so we're doing absolute values. So we're not looking at negative values. So if it's bounded, then this is what's going to happen. So if you take the limit of this function, so if you just look at, if you look at f of x as x over x plus 1, And then what would we say f of x approaches? So f of x approaches, well, if you just do this using some just algebra techniques we would have talked about, that just approaches 1. So that approaches 1 as x approaches infinity. So that's what's true for the sequence. So the sequence a sub n approaches 1. So this is then bounded by an upper bound. So there exists an m which could be like 2. So we know this is never greater than 2. That's like a for example sort of thing. So for example, we know that this function is bounded by 2. Let's just throw it out there. Could be something else. So if that's the case, or you can show that, let's just say you can prove that this thing's never greater than 2, and you know it's monotonic, then one of the theorems says basically that a bounded monotonic sequence has a limit, or the limit exists. So that's the concept. So bounded monotonic sequence has a limit. It exists. So it's always increasing or always decreasing, and you can show it's bounded. Now, that's not saying that like what the limit is. It's just saying that it's bounded. So sometimes just knowing that a function has a bound and you know it's monotonic, then you may not know what it converges to, but you know that it has a limit, or a limit exists. All right, some more concepts. Let's see. Okay, so we can talk about, I'm not going to get into this in detail, but there's something we can call an upper bound. I can actually write that better. Upper bound. There's what's called least upper bound. So upper bound, like there's some bound, it's like your m, there's some bound you can show, and then there's a least upper bound. So like you can show that there's a bound, say m here, but then the least upper bound might be that, might be a w or something. So the sequence does this, and then that would be, so it never gets above that. It always starts getting closer to w. Would be the least upper bound. Okay, and so that's some of the topics you can get into more later if you're studying more math, but I'm not going to get into that right now too much in detail. Okay, let's jump to here's what's something called, this one I'm just kind of throwing out there because it's an important one. This is called the completeness property. Completeness property. This one says if a non-empty set S of real numbers has an upper bound, then S has a least upper bound. So it's like saying it has to attain its least, so some sequence So if you have a set of real numbers, and you're saying it has an upper bound, then S must have a least upper bound. So it attains that, like it has to get there. There's the smallest one that exists. It's called the completeness property, and it actually there's a lot of study behind this, and it's hard to you can show that this concept is equivalent to a lot of other concepts. We won't get too much into that. I just wanted to throw that out there.